Greetings, fellow knowledge seekers. Ernis here, ready to yank another fascinating academic paper from the to-read pile and hurl it directly into your waiting ears. Today, we're strapping ourselves in for a deep dive into the universe of graph transformers, those miraculous machines capable of understanding relationships in complex data. Think of it like this. Imagine each of us is a star in a vast cosmic network, and graph transformers are the astronomers charting our connections. The paper we're dissecting today is titled, Unifying and Enhancing Graph Transformers via Hierarchical Mask Framework. The authors, Yuji Xing, Xiao Wang, Bin Wu, Hai Huang, and Chuan Shi, have essentially created a Rosetta Stone for understanding these graph transformers. They've found a way to make these systems more flexible and efficient. Now, you might be asking, Ernis, what's a graph transformer, and why should I care? Great question. Imagine a social network, a brain network, or even a network of molecules. These are all graphs, collections of nodes, the entities and edges, the connections between them. Graph transformers are a type of neural network designed to learn from these kinds of structures. But here's the rub, existing graph transformers can be a bit clunky. They often require specific designs tailored to particular types of interactions. It's like having a Swiss Army knife where each tool only works on one specific type of screw. Not very efficient. That's where this paper comes in. The authors propose a unified hierarchical mask framework. A way to see all these different graph transformer architectures as variations on a single, underlying principle. It's like realizing that all those specialized Swiss Army knife tools are actually just different ways of applying leverage. Let's construct a memory palace, shall we? Imagine a grand, circular library, a celestial rotunda where each alcove holds a different secret about this framework. Our journey begins at the entrance hall. This is where the core idea lives, the equivalence between model architecture and attention mask construction. Think of the architecture as the body, and the attention mask as the soul. They're inextricably linked. Now, mosey on to the receptive field room. Here, the authors show, through some rather elegant math, that the probability of correctly classifying a node in a graph depends on two key factors: the size of the receptive field, how much of the graph the model can see, and the label consistency, how similar the labels are within that field. It's like trying to guess what a person is thinking. The more you know about their background and the more consistent their behavior, the better your guess will be. From there, saunter through the hierarchical masks hall. This is where the magic happens. The authors identify three main types of interactions in graphs: local, cluster, and global. Local interactions are like your immediate neighbors, cluster interactions are like people in your town, and global interactions are like, well, everyone on the planet. Now, here's where it gets interesting. Listeners. No single mask is perfect for all situations. A local mask might be great for nodes with lots of similar neighbors, but it won't work for nodes on the edge of a cluster. That's where hierarchical masks come in. By combining masks that capture different levels of interaction, we can get a much more complete picture of the graph. Now, let's venture into the M-cubed deformer chamber. Yes, it's a mouthful. This is the author's proposed model, a mixture of experts-based graph transformer with multi-level masking and dual attention computation. It's a bit like a super-powered Swiss Army knife that automatically selects the right tool for the job. M-cubed deformer incorporates three hierarchical masks: local, cluster, and global, and uses a clever, expert routing mechanism to decide which mask is most relevant for each node. Think of it as having a team of specialists, each focused on a different aspect of the graph, and a smart manager who knows when to call on each one. To make things even more efficient, M-cubed deformer uses a dual attention computation scheme, dynamically switching between dense and sparse modes based on the local mask sparsity. Basically, it's a way of avoiding unnecessary calculations, kind of like only firing up the warp drive when you need to travel between galaxies. Finally, we arrive at the Hall of Results. Here, the authors present extensive experiments on multiple benchmark datasets, demonstrating that m^d former achieves state-of-the-art performance. It's like they've built a better telescope and are now seeing further into the cosmic network than ever before. So, what's the takeaway from all this? This paper provides a unified framework for understanding graph transformers, identifies key principles for mask construction, and introduces a new model, m^d former, that significantly improves performance. It's a major step forward in our ability to learn from complex relationships in data. Now, I know that was a lot to take in, but don't worry. The key is to remember the big picture. Graph transformers are powerful tools for understanding relationships in data, and this paper helps us make them more flexible and efficient. As always, my friends, stay curious, keep exploring, and never stop questioning the universe. Who knows what other secrets are hiding in those academic papers, just waiting to be discovered? Until next time, this is Ernis, signing off.